In the last video, we set up our first agent-based model by setting up a grid space single and creating a matching agent. There we experimented a little bit with initializing a model function by creating different types of models and adding agents to our model. Some of them were healthy, some of them were sick, and then we tested how we can have a look at these and saw that we needed a visualization. That doesn't make sense. We want to visualize this. So there is a function called model plot, ABM plot, sorry, ABM plot. And the ABM plot gets a model, and I think it requires some additional values. So let me quickly hover over ABM plot. It needs a model and it needs keyword arguments, and what it returns is a figure, an AX and an AB mobs. And we can also do ABM plot exclamation point, and that will change the axes, the model, and the keyword arguments. So let's do the most simple version. That is, let's do ABM plot model and see what happens. Nothing happens because no method matching ABM plot. Okay, what did we need? We needed keyword arguments. That should actually work. We only need a model and some keyword arguments. We should probably do, so what we saw there is it returns multiple things, and these multiple things were a figure, AX, and AB mobs. So let's store this. And we still have no method matching. What it says is, where is the first? No method matching ABM plot, standard ABM person. It tells me it doesn't have any ABM plot. Is that model, is that not loaded? ABM plot. Let's add a keyword argument, and things that we need are two functions. We need to have an agent color, and we can basically say the agent color should be green. We should have, well, let's say blue. We could also have an agent marker, and we say this is going to be a rectangle, and we should also have an agent size, and we just say it's 10. Does that work? No, it doesn't. No method matching. Did I unload everything and the model is no longer there? Let's test it if I run everything. No, it's still not there. So random task locator, this is not what is here. So we need to figure out how to plot our model. Where am I? Let's close the settings.json. ABM plot. Do I need this version of it? No, I don't think so. Let's figure out if ABM plot is available. It should be in the agents package. ABM plot, that is available. So let's test if this works. If I put this in front, then it will at least, then I'm telling it which version to use, and it doesn't work. There is no, oh, it says generic function with 0 methods. So ABM plot is loaded. Okay, but it doesn't have a concrete realization of it. We need to have a, and that's the thing in Julia, you can define a function and you have, which is a method, but it doesn't have a real implementation behind it because you might want to have different implementations. And one of these can be generated from, we can get from Cairo. Cairo is a plotting utility, and wait, I'm in the wrong terminal here. And I will add Cairo by going into package manager mode and say add Cairo and Makey. That is the visualization toolkit that we want to use, which includes, as soon as it's loaded, it tells agents to get the Cairo Makey version of ABM plot. And if there is no plotting backend available, it doesn't know which one to use, and that's why none of them are available. So while this is loading in the background, I'm giving you some nice elevator music. And here we can already see that installing Cairo Makey adds the agent's visualizations to the agents package. So there was a stub already available, so we had a method but no function. And now as we install ChiroMakey, agents will also receive a concrete realization of this ABM plot method, and we're using the one without the exclamation mark. So what does this do? Let's wait another 1 second. Okay, 7 dependencies precompiled, but different versions are currently loaded. Restart Julia to access the new versions. And that is a good idea to restart Julia. So we close Julia and we open up Julia again. And we run all of this. And for plotting, we're using ChiroMakey. There's different Makey versions, which are all tools to visualize something in Julia. We're using ChiroMakey because that is nicest for plotting. For videos, I think GLMakey is better, and for interactive versions, there's also, I think, GLMakey is better. We'll see this soon. So we're loading ChiroMakey, and this is now pre-compiling in the background. This shouldn't take too long. And now we're there, and now we should be able to call this function. Hopefully, let's see what's happening. It's doing something in the background. Yes. And the result of this call is a scene 800 by 600 pixels, axes, and so the reply is a little bit more complex. We have a figure, axes, and AB mobs. And what we want to have a look at is the figure. By now going into the figure, we now see a result. And if your result appears in Visual Studio Code, that's okay. I have deactivated this. I want it not to be inside of VS Code because for videos, this will not work very well. And if you have it inside of Visual Studio Code as a sub window, there's an easy way to change this. You go into Settings by going here on the cogwheel and then Settings. And then you can search for Julia and I think output. No, Julia panel maybe? No. Okay, let's look for it manually. I just go into Julia, and down here there is a thing, code in REPL, inline results, focus plot navigator. No. Linter, let's check for Julia plot. Use the plot pane. By default, this is active. And let me quickly show you what the difference is. If I do this, and let's see if it changes on the fly, it will create a plot inside of a pane. And this works for single plots, but it's not the best for interactive exploration. So if you have this active, remove it. It makes a lot of things easier. Okay, what have we done now? We have visualized our agents in a figure, and now this is a freely moving window, and every agent is blue. That's kind of boring. We want to see which of the agents is actually infected. So the way this works is the model is the one that's visualized, and AC is agent color, and currently I'm telling it to be blue by giving it the symbol blue. We should probably have a function dependent on the agent that tells it which color to use. So we can define a function called agent color, and let's call it person color because we're speaking about persons here. Person color, and that requires an agent, P in our case. And there is different ways of how we could define this. We could write function person P, and then if p.health equals 0, then we want to return blue, else we want to return red, red, and we have to end the if statement, and we have to end the function. So if I do this, and instead of giving it this, I can just give it the function person color. Important to note is I don't give it the parentheses because I'm just giving a reference to that function. I'm not executing the function. I can easily execute the function by doing person color, and I have to give it a person, so I can go model and pick one agent, and it will give me the color of that agent. That one is healthy. And the second one is healthy too. But this thing only wants the function and not the evaluation of the function. And I can get it by not putting in the parentheses. And what this now does is I can generate a plot and I can plot it. And there is this one little red square here that is now the ill person, where where the health is not 0, it will return red. However, there's a much more efficient way of writing this, and I'll show this here. Instead of using the function argument, we can just do it math style so for example, if you define a function in Julia, f of x equals x squared, this is the same as defining a function f with a parameter x and returning. So this is equivalent to function f of x return x squared end. This is the same thing, it's just written in math style. And if you have a short function that fits in a line, you can basically put the person color in a line as well. And we can easily do this by doing person color equals p.health equals 0. And now we do the ternary expression again. So if that is the case, we return blue. Otherwise, we return red. And this looks a little bit complicated, but once you understand what it does, it basically says you have an if statement, and this is what's evaluated. This is the defining operator for the function. This is the expression that's being evaluated on that parameter p, and if that is true, we return blue, else we return what is behind the colon, and in this case, red is also started with a colon because it's a symbol. But that does exactly the same as what we just had before. So we can now get a figure and we get the same result. We could also increase the size. Let's do maybe 20. How does that look? That looks a little bit better to read. We can do 25. Yeah, so these are our agents and this is the ill agent. Okay, we have defined all of them as rectangles. We could as well do circ, I think is for a circle if we want to, but I think rectangles look nice. Let's use the rectangle in this case. So down here we have plotting, and we can now plot a model in any state. If we have more infected people, we will see more infected people. But still nothing is happening. We just initialized the model, and wait, this belongs also in plotting. So all of this is only plotting. So this is functions for plotting, and this is the actual plot a model. So let's move this a little bit out of the way. We're going to need this later. At the moment, we only have one person ill, and that doesn't do anything. We need to evolve the model, and for that, for some reason, there is a... Whoops. Where am I here? Okay, we have a standard ABM with 400 agents of type person. What we need is we have to call the step exclamation function, which gets a model, and now it gets an agent step function, agent step. But we don't have that agent step function yet, so it's not defined. We have to define it. And whoops, we can do this by doing function agent step, and at the moment it doesn't get any arguments and it doesn't do anything. And if we call it, this doesn't work. And the stack trace is a little bit more complicated. It says no method matching agent step person standard ABM grid space person type of blah blah blah. There's a lot to unpack here. So what this basically tells me is I did find a function called agent step, but it's not the one that I expected. The agent step function requires a specific set of arguments, namely a person, and I think the rest is probably, yeah, it's a standard ABM. It requires a model, and in our case, a grid space single model, so we can just do model. So if we do this, we have a function. It still doesn't do anything with the person or the model, but now it has the right signature. It is applicable in this case, and we can now advance our model. We can advance it 100 steps, and it will do nothing because our agent step function does not do anything. So behavior. Here is where we actually do the behavior. And the behavior is performed on an individual person. So what we need to do now is we need to determine whether this person will get ill. And we can find this out if one of the neighbors is ill. So what we need to do is we need to look for the individual neighboring agents. And how do we do this? There is a function called nearby agents, and this gets me all the agents that are next to this person. This is kind of hard to understand because we're inside of a function. So what we will do is we will basically copy the code down here, and we will get a person from our model by just doing the, yeah, let's do this. The person that we get is agent number 1, and it's in position 1419. And if I do nearby agents on that person, that doesn't suffice. We need to have the model as well. I think, yes. And now we get a weird result. It's a base generator, base iterator, filter, blah, and so on. So what Julia does in the end is it doesn't give me a list of the agents. It gives me a generator. And what a generator is, one thing that you possibly have seen is this. This returns the values 1 to 10. This is a generator because we can do this. This is all the numbers from 1 to, I don't know, something, but it doesn't store all the values. It just tells you this is a generator, and if I put this into a variable, let's call this p, I can now access this variable, and the generator tells me how to generate the number for this index. So this is an array that has so many entries, but it doesn't store these entries because it has a way of generating the entries from the index. And the benefit of that is this would, if I were to store all these numbers consecutively in memory, I don't have enough memory space for that. So this is a more efficient way of storing things and only waiting until you access those things before they become available. It's kind of like a proxy element that waits to load the data until you access it. And this is what the generator in this case is as well. So if we store this in a variable called neighbors, we now have these neighbors and we could now try to access them, but this is not a indexed neighbor. There is no numbering of them because there is no order in them. It doesn't mean there's a first neighbor, a second neighbor, there's just a list of neighbors. And this means we can get them by calling the collect on the neighbors. And this will return now a list of these neighbors. And we will see the neighbors are on position 1318, 1418, 1518, 1319, 1519, and so on. So these are the 8 neighboring people. By the way, collect also works on this, and this will give you a 100 element vector. And you will quickly see the larger you do this, the more problematic this can become because this will take a lot of memory if you make it very large. So I don't know if this works. Yeah, this still works. This now takes a while. But if I would not have called collect, if I had only done this, this would be fast, but it's still running, I guess. Is it still running? Yeah, it's still running. Let's cancel this before it crashes my machine while I'm recording and memory is going low. Trash can. So let's remove this and just do all of this. And so what have we here? We have nearby agents is a collection. Lots of agents are in there. I can do the collect things to go over them, but it's even easier. You can loop over the individual elements in there without collecting them by going for neighbor in nearby agents, and this will now go through all the individual neighbors in this. Wait, this requires the model. And we can, by doing this, we can go through the individual neighbors and ask them questions. So we could now do neighbor.health is equal to 1. So if that is the case, if the neighbor is ill, then you should infect the person with a certain likelihood. So here we would have to throw a dice to determine whether or not that person should get infected or not. We do have the model susceptibility, and that is 0.3 at the moment, but we want to make sure that only in 30% of the cases we have this. So there is the random function, and if we call the random function alone, it returns a value from the uniform distribution from 0 to 1. So 0.63 is the value that we have. If I do this again, 0.9, 0.38, 0.4. And this value will be smaller than 0.3 30% of the time. So this expression here will be true 30% of the time. You cannot determine which ones, but it will be true 30% of the time. And this is a typical pattern that you see by calling the naked random function and comparing it to a threshold, which will enable you to have this occur as frequently or as often as you determine its probability in here. So what we could do here is, if we have an event that occurs as frequently as this model susceptibility is determined, then the agent himself or themselves should become ill. And if we do this, we now have an agent step function. And if we do, let's do only 3 steps. If we do this, agent not defined. Oh, the thing is not called agent, it's called person. So let's redefine this, not collect this, do this, and let's plot the thing again. Person color not defined, oh, because I restarted, okay. I have to reload ChiroMakey, I have to reload our person color function, and after that I have to reload the plot, and I can then plot the plot. And as soon as it's ready, we will see, yeah, this is the infection that has occurred. So after 3 steps, so many people have become infected. And we can basically go back to model initialize and do a plot. This is the first agent that has been infected. And we can do, let's do 1 step and see now 30% of its neighbors should have become infected. And that can be 0 because it's probabilistically 30%. Let's do another step and see what happens now. And in this case, oh, that's an interesting thing. One thing to keep in mind is this person was infected first, and he infected in this step these people, possibly also not this one. But as soon as this one was evaluating their neighborhood, these 2 people already got infected. So a thing that can happen in this infection model is that it spreads super quickly because of the order of how these agents are being evaluated. And that's an interesting thing. The agent step function works while it is running, and this means we can have very, very rapid spread. Even 1 single step can now cause a lot of spread in the disease. And I mean, this is nice, but wouldn't it be nicer to see what happens if we see this animated? How the disease spreads. And there is a tool for that. And for that, I think we have to use GLMakey. And while this is installing in the background, I will add GLMakey. I will let you know how this works. So what we need for that is we have agents.abm video. And this can generate a video from a model, and it also needs the agent step function. So it requires 2 things. It requires the model and the agent step function. The video itself is stored in a file, so we need to give it a file name, and in this case we just call it our model.mp4, and we give it the agent step, and we should probably tell it how far this should run. So we can say, let's do 10 frames, and we have to give it a frame rate. And in this case, the frame rate should be maybe 1 frame per second. So what this does is, frames is how many steps of the agent step function do we want to render, and the frame rate says how many of them should be in a second of video footage. So this creates a video that takes 10 seconds, and let's see if this works. Can we load GeoMakey when we have ChiroMakey loaded? Yes, we can. And if we do this, agents ABM video, this takes a while because it requires all kinds of things in the background. But here we have it, our model MP4, and we can run it, and nothing happens. The reason for nothing happening is we didn't define what we wanted to see. So the default color is purple, and the default size is 10, and the default shape is a circle, and what we want is this. We want the person color to be in here as well. And let's organize this that it becomes more readable. So this is, here we have the model and the file name. Here we have the coloring options and the drawing options. Here we have the frames and the frame rate. And let's open this and let's start from the beginning. Oh yeah, that's also an interesting thing. Because the model is changed, now nothing happens. We started with a model where already lots of people were infected. So before doing the video, we should reset our model. And we do this by calling the initialize function. So this will give us a clean model, and this will generate from this clean model the video. And this is how this works. First step, second step, third. Oh, the video hung for a second. So in 10 steps, we have everybody infected. It starts from 0. That's why it doesn't go to 10. So we have to do maybe 11 frames, and then we should have everything in there. Oh, and obviously, that's a thing to keep in mind. We should reset the model before we run the video again, because the model is being changed by the ABM video function. So here we are. This is where it starts, and we can see the disease, in this case, doesn't reach everything. And that's another thing to keep in mind. Every time we rerun the model, a different person is infected the first time. We see this in the figure. Do we? Where is the figure? Can I do figure? I can't for some reason. Maybe because I overloaded GeoMakey. Okay, so now I think I have to reload ChiroMakey, and then I can do this again. I can't. Is it lost somewhere? Display. This is the one. So, because it was still open. The important thing to keep in mind is whenever I run initialize, it's a different agent that becomes infected, because the agent is chosen at random. And we do this here where we get a random agent. And that's not what we want. We want something that is a little bit more predictable, because otherwise, if your experiment depends a lot on randomness, no one else is going to reproduce what you can do. I mean, you do want non-deterministic features, but you don't want everything to be random. And one idea to achieve this is to give it a random number seed. We can do a default seed would be, I don't know, 1, 2, 3, 4. And here we would have to generate a random number generator. We call this typically random number RNG. And the Xoshiro is one that's frequently used, and this one gets the seed. And if we do this, we need to have it. And to have it, we need to add random. And random provides these predictable randomness things. So we can do random here. And now we should be able to do this, but seed is not available, so I can quickly define seed so that we... And the random number generator is now something that we can put into the model, and we do it like this. RNG is assigned to RNG, and now the model has a random number generator. And the random agent, I think it will automatically take the random number generator if the model has a property called RNG. I don't know, maybe we need to define it here. Let's see, does agent-based model have a random number generator? What is the definition of ABM? Is there, can I see the definition? No. ABM. Let's do agent-based model. Do we get a definition for that? Yeah. So ABM is just a shortcut for agent-based model. It's the supertype, blah, 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 whatever, whatever, we don't care. Properties, scheduler, okay, it gets the parameter of RNG. It by default takes a random default RNG, and that is not the one we want. We want to give it a specific RNG. So we don't do it here. We don't provide it as a property, but we do it here. So the RNG is the RNG. And if the model defined here has this parameter RNG, now all the functions that use randomness use this random number generator that is derived from this seed, and that makes it predictable. Not here. This random is not using this random seed, so we need to tell it to use it, and we can do this by doing model.rng. So if whenever you have random, you want to put in the model RNG as a first parameter to make sure that it is using the random number generator. And if we now, one thing we could do is close Julia, and if we press this play button here, it will now run all the code from top to bottom, including video generation. And the videos now should always look the same because we do one step in the beginning, yeah, and after that we reinitialize our model and do a first visualization. It takes a while to activate. There it is done, and now we can see this model. This is the version that we have generated. For some reason it gets stuck if I remove my mouse cursor, but I can do, this is the way, try to memorize this. This is how it spreads. And if I do all that again, it's now done quickly because it's already loaded. The model, if we reload the file, it should be the same, and it depends only on the random number seed. So I can here do this seed equals 1, and this will now be a different model. It will have a different randomness involved, and we see it already. It's a different agent that's infected, and we see a different spread. We can now have different starting conditions simply by going through different random seeds. And we can guarantee that our model is reproducible by making sure that people use the same seed as we do. And what we now have is we have our first little model. Let's move this out of the way. We have an agent. We have an initializing function that has a space, that has a random number generator. It returns the model. We have our basic behavior. We can, we don't have to test it manually. We can do this in our video version. Generate a video, and we can plot. Maybe let's put this up here so we have it for a figure, and we have it as a video. And that is what we get from this. We can also, by the way, also give this a title. This is also helpful. Title is our first model. So if I do this, this will add a title to the plot, which kind of looks nice. And obviously we can run it for more steps. We can increase, go up to 200 frames, and we could go to a video-like quality to going 30 frames per second. But the challenge with that is, if we run, well, we can run all of it. It should be relatively fast. We should now have a shorter video. TOML files. Why does it want me to? No, let's not do that. And this should be very quick. Zoop, everyone is infected, and it runs for 200 steps. And this is where we already see is people don't get healthy again. They turn from, what we now have is from this model, an SI model. This is an SI model. But we want people to become healthy again because, it depends on the disease that you're modeling. But my idea here would be to have an SIS model. And the SIS model requires that we keep track of how long a person is ill. And we already prepared for that. We have an illness duration. And in the agent step function, the first thing that we should do is when a person is ill. So this is how a person gets infected. And after that, we should test if agent.illness duration. Oh no, let's first see if they are ill. If agent health is 1. So what happens with all the ill agents? We increase their illness duration. Agent, is it agent? No, it's person. Person dot illness duration. We should increase this by 1. So now every time we count how long has this person been ill. And in this case, we wanted to have a fixed illness duration of 10 days. So what we can also test is if this illness duration, as a result of this, if person, we don't need parentheses, if illness duration is larger or equal than 10, then model.illness duration, which is the parameter in our model, which we can change from the initialize function, then we should make that person healthy again. Person.health is 1, and we should also make sure that his illness duration counter is reset because the person is healthy again. And what this now introduces is people will get healthy after 10 steps. Try to make a prediction of how this will affect the model. Will everyone get healthy or not? I assume you've made your prediction, so let's test it out. We run this model. We can have a figure. We are not really caring about the figure. We want to see the video. And the video runs for 200 frames at a frame rate of 30 seconds. And let's see what happens. Did you make your prediction? Good. What we see is waves. So people will get healthy and the wave of healthiness expands, but people will get reinfected very quickly. There is no immunity or anything like that. People will just get healthy again over and over again. So we don't have an SIRS model where people are recovered and for a certain amount of time stay immunized to the model. We have an SIS model, and that's okay. Let's keep it this way. We want an SIS model. And the reason for that I'll explain in the next video. One neat little trick I want to show you is this is how people typically write larger or equal than. But if you're familiar with LaTeX, you can also write larger or equal than, then press the tab key, and this will, oh no, that's less equal. So it's not larger, but it's greater or equal than. Is it? GEQ? Yes. And then it will insert the UTF-8 character for that, and that evaluates the same. So this is the same as larger equal. And yes, this concludes this first session on creating your own agent-based model. I realize this was fast, but the idea is that you try to recreate the model for yourself, and in the next step we will add an additional layer to that. And we will see first how to evaluate these models, what the influence of these parameters are, how many agents are in a space. We can test the effect of all these parameters in the model, and how to do this we will see in the next video. And I'll see you in the next one.